Welcome. So I'm Martin Schwenke. I've been well introduced, so I don't really need to go into that sort of thing. I would note that there are 3 other very good talks on at this time, so if you found yourself in the wrong place or you think that testing will be thrilling, you might like to reconsider. 3, 2, 1, thank you. And this is Ronnie.
Hi there, Ronnie Solberg. I work with Martin and we work on this really cool piece of software to build really big and massive servers. As working with big systems is not entirely trivial, so Martin will go through a presentation here to talk about, well, what do we do to actually test it, if it works before the big bank goes down.
Okay, and yeah, we both work for IBM at the Linux Technology Center, and we have a lot of fun, and there are a lot of penguins. Okay, what are we going to talk about today? Well, we might as well start off by telling you what CTDB is. That's going to be useful for the conversation. We're going to talk about what needs to be tested, and once you know what there is, what needs to be tested is pretty trivial. We're going to talk about an old test suite that we have. Test suite is in inverted commas because it doesn't test that much. We're going to talk about testing CTDB's event scripts, which we'll tell you what they are. And we use a whole bunch of stubs for that. And then we're going to talk about CCAN style tests for the C parts of CTDB, which is most of it, and give a couple of examples. We're going to mention AutoCluster, which is cool for generating clusters of virtual machines on your laptop or hopefully on a real, on a nice server. And we'll talk about performance testing with dbench. Ronnie, what is this CTDB thing?
Yeah, ctdb.samba.org is the homepage. It's open source. Basically, it is a very fast but lossy cluster database that's used to store server metadata or in the internal server state for example, Samba. Samba needs to keep track of lots of stuff inside memory, but then when you spread Samba across a cluster of, say, 20, 30, 40, 100 nodes, it's really important that all the Samba processes, well, they agree on what the current state is. And that is the main part of CTDB, to provide a clustered version of this trivial database that Samba uses for the internal server state. We use it to build all active multi-node clusters. As you saw in some earlier presentations, who has a server with 4 terabytes of memory? We do. Spread across, well, more than one motherboard, of course. It's a database. It has basic monitoring. Is this piece of hardware working or not? Should we do failover? And we shuffle IP addresses around the cluster in order to try to load balance the clients. For more information on this, Tridge, as always, have created an excellent presentation, and there are some videos from an earlier LCA you can watch.
Okay, so the dumb question of what needs to be tested, well, that's everything. We've got a daemon that sits there and it's got a bunch of C code in it. We've got some event scripts. The event scripts are things that CTDB calls out to interact with a service or to monitor the health of a service. And these things are just nice little shell scripts. And sometimes we make rather large changes to them and we want to be able to test them and make sure that they still work. So we need regression tests. We've also got a CTDB tool that lets you interact with the daemon and interrogate it for status and send it configuration foo. And we want to make sure that tool is doing the right thing. So there are lots of parts. Previously, as I'll talk about in a second, we had a test suite that tried to test everything at once. When something fails, how do you know where the problem is? Well, the obvious thing is to unit test. If anyone's ever done software testing, you know that if you want to find the bugs, you do unit testing. So what we're trying to do is we're trying to basically every time we change a chunk or a subsystem in CTDB in a non-trivial way, because we currently don't have tests, every time we make one of those changes, we go, okay, now's the time to write a little test harness for this, write some test cases, and especially test that the bug we just fixed is fixed, so that next time somebody touches that code, we don't get a regression. It's pretty obvious stuff. As I said, there are other good talks on at this time. We also want to check for performance regressions, memory leaks, file descriptor leaks, all the sorts of things that make software go bad.
This is not always entirely trivial, because when you have a system spread across, say, 100 motherboards and gigabytes per second are flying everywhere, it's very difficult to make a test to repeat things in an entirely deterministic way every single time.
So yeah, so we're better off doing unit testing to test the basics. We have this old test suite which tests the basic functions of CTDB. Somebody else working on the project we work on specified these tests. So we have this daemon that does a clustered database. We have all this fantastic functionality, and then we have a tool which has a bunch of verbs. You say, you know, CTDB ban this node, CTDB get var to get the value of a configuration variable. And somebody thought that the best way of testing CTDB was to write tests to test that all these verbs work. Whether CTDB's database is actually storing the data in a useful way apparently wasn't considered too much. So we wrote this test script, and some of the tests were stupid. And since we've been really busy over the past couple of years, we haven't actually been adding tests. We've been removing the stupid ones. So our test coverage has actually gone backwards. There are a few failover tests that test sort of gross system failover. If I connect to the Samba port and then I mark the node unhealthy, what happens? And there is one thing that this test suite is really, really good at, and that's finding bugs in the startup code. Because every time a test runs that changes the state or changes the configuration of the cluster, we restart the CTDB daemons on all nodes. And if we do that 15 or 20 times during a test run, we soon spot the races. And so this test suite has accomplished something. The other thing that Ronnie does is, as maintainer, he's got a suite of manual tests.
Manual tests. Every time you spend 1 hour writing code, you spend 8 hours running the code through Valgrind and GDB, and so, well, you try to trigger every single code path at least during development testing so that you know that it has been traversed by an executing program at least once. Sometimes that's really, really difficult, so you have to, well, deliberately add bugs in the code so you can trigger these error paths. Most of the time you remember to remove those breakage from the code. Sometimes you don't. So where we're sitting, you know, here, which is probably 6 or 12 months ago, is a pretty sad state of affairs. We've got a really complex piece of software. We've really got no useful automated testing. So what do tests in the old test suite look like? Here's a snippet. Sorry, we're missing the first column. So it's an exercise to try and determine what the contents of the first column is, but that's just the way the projector works. It's partially proprietary code.
That's good. Just for a hint, and I'll only do this once. VTVEITETNI. Right. Okay.
Can't you put a space in front of every line?
Aha. No, that's not. Is anyone here an Emacs user? I am. I've hacked on it, but how do you get line numbers in your buffer? Yeah, okay, good. That's a really good question, and I'm glad we share that question.
Meta C, meta M, meta C, meta butterfly.
No, that makes butterflies fly on the screen. Okay, so our tests, and all of our new tests are shell scripts, apart from the things that actually need to call into C code, because they're easy to hack. And also that means we've got no infrastructure. If our tests are a shell that comes with the operating system, then we can do an install and we can do a test on a new install. There may be better options. We get the value of a configuration variable called recover timeout. We know it's numerical, so we add one to it, we set it, we get it back. and we make sure that it's what we stuck in there. It's a pretty dumb test, right? But it tests something. And we can run that test and a bunch of others. And I mentioned that when we run tests, we restart CTDB a lot. It takes a little while for the cluster to become healthy after we restart all the nodes. And this is the first pseudo test that makes sure that we're in a state for the following tests to continue. So, after about another 10 more dots, you're going to bet on 10, 11, 12 dots. It'll kick off and start running the rest of the tests, and then we won't watch it anymore because it's boring. You came here to watch tests being run, didn't you?
This framework is pretty intelligent as well. Now Martin is running it with multiple daemons running locally on just his laptop, but with a couple of minor tweaks, all these tests can also be run on a genuine cluster, either a physical or a virtual cluster.
Yep. Alrighty. Event scripts. Is that me or you?
Take half of it each.
It's me, isn't it? Oh,
yeah.
I can't remember. Okay, event scripts. Okay, so these are just shell scripts. And the first argument tells the script what it's doing. We'll have a look at an example in just a minute. They monitor the health of a service or something to do with something important for doing NAS, such as your network interfaces. And how do you test that? Well, there are a lot of system commands, so you just write a lot of stubs for all of those commands. That seems like a good idea. And event scripts use the CTDB command line tool as well, so we write an enormous, horrible stub version of that, and we fake up state when we do our setup. It's the ugliest thing you've ever seen. It'll get better in the future. So we've got all these event scripts. They're pretty complex bits of shell code. I rewrote hundreds of lines of this stuff. We had no tests. What to do? Well, make some changes to the event scripts and write some tests. So the whole idea is that for all of these system commands, you write a complete, no, you don't write a complete re-implementation when you're doing stubs, do you? No. You only implement the parts that are interesting for your tests. And that's what I thought about this talk. Oh, you're not leaving?
How do you make sure that you're not running unstubbed versions of things?
Then the tests will fail.
Yes.
Sorry, something I meant to mention. Well, we'll see. You modify the path to put the stub directory first, and if there's something you haven't written a stub for, then so the CTDB event scripts control the path. And in the test infrastructure, we control it a little more. Now, the whole idea of all this unit testing is, the first one thing I meant to mention about the old test suite is that it has to run as root, because you have to be running CTDBD. One thing about this is we want developers to be able to type make test, run the whole regression test suite. It's not set up like this yet, but you run the whole regression test suite as you, the developer, and it can stop at the first failure. So, and the good answer there is that if you end up using a non-stub version of some command because none has been written, then A, the test should fail, and B, because you're running as yourself, you haven't destroyed your system. You might only destroy your own data. So there's no real smarts in there for that. Okay, this is the world's simplest event script. The first argument to the event script indicates the type of event. If we're starting up CTDB, we run CTDB service start. If we're shutting down CTDB, because CTDB is managing this service, we run CTDB service stop, and there are some configuration variables and functions that tell it what to do for each of these. And then for monitor, we just check a Unix domain socket. And if the socket either isn't there, see, I don't know right now what CTDB check Unix socket does, but if it's checking for the existence or It's checking that netstat conceit or something. If that fails, we exit with 1. The event script monitor event fails. CTDB on this node gets marked as unhealthy. We fail IPs off this node onto other nodes. So simple health checking, very simple event script. Next, no, you hit that key. Okay, so here's a snippet of one of our event scripts. Well, it's the editor looking at one of our event scripts. And this checks the health of interfaces. How do you do that? Well, that's pretty boring. You run ethtool against the interface, and if you see the string link detected : yes, or link detected : s, it's meant to be a Y there. That's an important feature here. Then everything's okay. Otherwise, you try harder, and finally you say error, no link on the public network interface. So not terribly interesting. But this one thing about the test cases, so this is one of the test cases, D-S-I-E-R, you'll get it. One thing about the test cases is that they are nice and self-contained. There's a bunch of helper functions, and we do set up CTDB, which fakes a whole lot of state. And it sets up a bunch of interfaces. We don't know what they're called, so we write a function that gets one of them. We mark it as down. And then when we run our event script with the monitor event, we're meant to get an exit status of 1 and that error. That's pretty simple. So how do we fake ethtool? That's the whole script, right? We don't need any more of ethtool than that. When we mark the interfaces down, it creates a really stupid flag file that means this interface is down. If it exists, link detected is no, otherwise link detected is yes. A slightly different thing where we can't just modify or create a stub. This is exactly the same example, except that we're setting up a bond. How can we tell if a bond's up or down in Linux? Anyone? Sorry? Right. So the answer is we look at procnet bonding blah. And if we go back to this script, and here's the obvious answer. Before writing the test suite, we actually just catted procnet bonding interface name. If we're not running as root, we can't do that. We could do some LD preload magic, but instead, in this case, because we're only looking proc less than 10 times in the event script code, we write a function called getProc, which on a real system looks in proc. In our test environment, it looks where we drop the file, the fake procnet bonding interface name. So it's not terribly exciting, but we have the decision of whether to do something tricky, like use an LD preload or something else, or just modify the code. And in this case, to enable testing, modifying the code was a good thing. I think our time is up. There's an alarm going off. That's all right. Okay, let's go through to there and right. So another piece of CTDB that we want to test.
IP allocation algorithms. We have very, very many nodes. We have very, very many IP addresses. By distributing the IP addresses across the nodes is a way we can control the load sharing of the workload that the clients generate. This is reasonably complex, and we had an old algorithms that didn't really work that well in the cases we needed it to work. So we came up with a new, incredibly complex, beautiful algorithm, so complex that we don't even really understand how it works. How do we test that? First, we implemented it the algorithm in Python, and in Python we wrote the simulator to simulate a cluster of X number of nodes, 2 nodes, 4 nodes, 100 nodes, and then we generate random node crashes. Maybe we crash 10 nodes, bring 5 nodes back, crash another 20 nodes, and at every single stage the simulator goes and checks this algorithm, when it has rebalanced the cluster, does it look sane, or is there something we should have a look at? That worked reasonably well. We rewrote the code in C, implemented it in CTDB, continued testing, but since we already had a simulator where we had tested a different implementation in Python, Martin did some really smart stuff there on the next slide. How can we use this Python simulator to exercise the code that sits inside the daemon that is written in C, so that we can also run this failover simulator, run 10 million failovers on the genuine code?
So you end up with a decision about, you've got a static function in a C file, in a whole lot of code. How do you test it? Well, one option, the first thing we did to be quick and dirty was we took out the keyword static from before the function, which means we can compile the .c file and then link to it. And then we sort of thought to ourselves, well, we're going to need more of these things. So we're probably going to build most of the code from CTDB into a shared library. That's going to be fun. And every time we want to test a new function, we're going to take out static and we're going to mess up our code.
The shared library thing, that was my idea.
I can't, but it was a good one.
Yeah, that's why we're not using it.
Well, okay, we now sort of segue into the mid-presentation entertainment. We have a live fist fight. Anyway, no, I won't say that. Okay, so I was having so this seemed like a really good idea, and we were going to do this, so Rusty Russell has come up with this CCAN project, and you know, it's a place for putting good snippets of C code, and it's meant to end up, you know, huge and wonderful like CPAN. And I was chatting with Rusty, and he said, and I was telling him about this shared library thing, and he said, no. Just hash include all your C files. That's how we do it in CCAN. It's a really cool idea. You can access your static functions for free. Of course, if you have the same static function in 2 C files or a different implementation with the same name, because you don't have, you know, because you've got nice lazy naming conventions as most of us do, you try to hash include all that C code and you get a compile error. So you spend a couple of days cleaning those up. They're pretty easy. There wasn't that many of them. And then you can hash include a few little C files so that you can run your examples. And it was really easy to write a test case for the first bug that got reported back to us in the new algorithm. So let's have a quick look. So, how many things would we like to hash include? Well, perfect. How many things do we need to include? Well, you include the standard stuff that you include at the top of CTDB files. And then there's some stuff out of the file that includes main that we haven't quite cleaned up. So we need to redefine those things to do something or nothing, a couple of variables and a function. And then we need to include a few C files and a few more C files and a few more. We have lots of memory on our systems. We don't care how big, well, it doesn't matter how big the binary is, does it? We've got lots of disk space, is what I really mean. We end up with these big binaries, but we don't care because this is easy. And then, in this file, we can include the previous C file because it's doing all the includes for us. And then we've got a very, very simple way of testing our function that we want to test called CTDB takeover run core, which is in the middle of the screen. Above it, we've got CTDB test init, which takes a whole bunch of fake state on standard input, parses it, and sets up what looks like enough CTDB state for the takeover code, for the IP allocation code to run. We run the IP allocation algorithm, and then we print out the IPs and what nodes they're on. It's, there's certainly no rocket science here. And so once we wrap that in some test code, we have an example where we've got a bunch of IP addresses, all on the 9.2 network. We've got 3 nodes, which are at the end of this little test run are all going to be healthy, indicated by 0, 0, 0. And all our addresses are currently sitting on node 1. And the assumption here is that node 0 and node 2 are unhealthy. And then what we expect after we run the test is that all of the IP addresses are evenly spread over nodes. And when I count, I see 3 addresses on each node or something similar. And we're happy. So, and then, a slightly more complex example where we want to read in a bit more state, and this was actually the bug that got reported to us. We've got 4 addresses which can go on nodes 0 and 1. We've got another 2 addresses which can be on nodes 2 and 3. The addresses for nodes 0 and 1 are nicely spread over those 2 nodes. Currently, out of the last 2 addresses, they're both on node 2, therefore node 3 is currently unhealthy. And then, when we run it, we of course expect one of those addresses to go to node 3. I could run the test for you now and show that it's fixed, but I wouldn't be standing here if it wasn't. So straight away in about 10 minutes we had a regression test for the bug that got reported, which is nice, which was better than the previous situation where we had no regression tests for anything. What else is here? 29 minutes. More examples? Nah. Should we talk about libctdb? Do we have time? Should we discuss it in front of people?
No.
No. Okay.
Go with AutoCluster. AutoCluster is a brilliant piece of software that is useful not just for this, but for any time where you want to create a cluster and you only have like 25 seconds to configure, reinstall Linux, configure everything up and boot them. That's when you want AutoCluster. A brand new cluster like that.
So yeah, the nice thing is, if you've got a cluster, even an old virtual cluster sitting around and you've been doing testing on it, it bit rots and you don't know what state it's in. And what you really want to be able to do is take that cluster, virtual cluster, throw it away and build a new one in a matter of seconds so that you can have a new cluster for each set of new tests. So this is the idea. This is something Tridge wrote in a weekend and then handed to me to continue to add options. And I can proudly report that at this stage it's got more options than rsync. So it's a tool for testing clustered Samba, and it's just a bunch of shell scripts. Bash, because POSIX shell just wouldn't support some of the lunacy. And we create virtual KVM-based clusters. This is the topic of a talk I did at LCA 2009 with Tridge, so the charts are hanging around on Tridge's site. So if you've got heaps of interest, feel free to have a look and ask questions about that. I've added a nice new template-based service configuration system in there because we had a canned configuration, but it kept on bit rotting. So now we've got this template-driven thing, which is wild. And developers of CTDB and clustered Samba, clustered NFS can use this for testing. And also, at some point for the testing of the product we work on, I was surprised to hear that suddenly a whole bunch of the regression testing had moved to clusters generated by AutoCluster, which was kind of scary. So the first thing to do is start that, and then, so let's say you want to create a new cluster. We have a command to do it, and so the first thing that we do, which we're not going to do now because it takes 10 or 15 minutes and we've all got better places to be in a while, is we create a base image. So we throw a configuration file at AutoCluster and we tell it to use an ISO image to do a kickstart install. So right now this is limited to RHEL and CentOS, and this is the first CentOS one I've tried. And you do an install, you do a few tweaks at the end in a post-install script. The install finishes, Kickstart says, I want to shut down now, and you go beauty. It goes to shut down or reboot, and then you shoot it. And you've got a disk image containing a pre-installed operating system. Then you come along and you run something like AutoCluster, here's my config file, m2.autocluster. I can show you the config file, but it's boring. It's a bunch of environment variable settings. Looks a bit like line noise. And then we say create cluster m2. It uses guestfish to, well, first of all, it creates a copy on write image on top of the base image, and then it uses guestfish to mount the file system image, and then it installs a whole bunch of configuration files to distinguish that node from the other nodes in the virtual cluster. And in about, I don't know how fast I've been talking, it's probably going to be more than 30 seconds, we're going to have a brand new cluster that we can play with. But because I've used CentOS, and then we can add those 2 or 3 lines to the hosts file, and we can SSH to the nodes in the cluster, because AutoCluster has also snaffled root's SSH key and put it in the authorized keys file. And everything works nicely.
And as you saw now on Martin's laptop, it took less than 1 minute to create a brand new cluster from scratch. And this is absolutely brilliant. It's like when you learn to use Git first time, you start with branches. Every time you want to do something, you create a brand new cluster from scratch. So you don't have to sit and debug for 5 hours and discover that, oh, it was this temporary tweak I did on the cluster yesterday. Instead, you destroy the cluster, you create a new cluster, you do your stuff, and every single time you do something new, it takes less than a minute to create a brand new cluster that is in a guaranteed known state. Absolutely brilliant stuff. You should use it.
And, well, the other place this is really good, and you can write, well, say you wanted to write a build system, and you wanted to auto-build the piece of software that you work on, or you just want to test it, and you just want one node. Well, this is a hammer. So, you know, you can figure out how to drive libvirt or KVM or whatever yourself, but this thing creates one node clusters really nicely as well. So instead of trying to configure the cluster that we just played with and make sure that CTDB is installed and all that junk, here's one we prepared earlier, and we can run, you know, the tests we ran earlier. But this time, instead of running 3 CTDBDs on my laptop, I've got 2 virtual machines. Each is running CTDB. They actually talk, you know, they talk over the virtual Ethernet, and eventually the cluster should become healthy, and we should see tests starting to be run. Now, is that the... So while this goes on, we can check the status of CTDB and that sort of thing. And now, you know, the cluster should be healthy, and our really boring old test stuff that requires root to run runs on our cluster and runs all of its little tests. And it's not terribly exciting, but it shows that I can have a small virtual cluster. I had it running with Lotus Notes on the same laptop, which was pretty good. So, and then for performance testing, there's
dbench. We use dbench in automated regression tests for performance quite a lot. So after every single new version, we actually test whether or not we have the performance that we expect, or if we have had a performance regression. dbench is also open source. It's a load generator that can be used to describe any kind of I/O workload that you can imagine. You can replay the same workload using any number of virtual clients. We primarily use it for SMB, so we can replay a genuine CIFS workload to a cluster of Samba processes and see how does it perform when I have my 5,000 clients on this version. It allows you to detect when, for example, some component breaks OOP locks for Samba, so that performance drops by 90% before you ship the code to a customer, which is a nice feature. We can also do iSCSI and NFS testing in a very, very similar way with dbench. I won't go through any more of that, but it's very useful for automated regression tests for performance. The previous tests have all been to test correctness of the implementation. This is more a performance regression for the entire end-to-end application.
And every good presentation ends with conclusions. Well, we've now got some testing, right? CTDB is pretty complex. What sort of test coverage have we got now? 10, 15%? So we still haven't got great test coverage, but at least we've got we've used a few little tricks which aren't rocket science and, are known to most people who write software. To get some basic testing going and some basic regression testing. We use tools like AutoCluster and dbench to do the system level testing. And well, one thing we forgot to mention is there are a whole bunch of people in various parts of the world system testing the entire product that CTDB goes into. And they're testing these clusters with real people sitting there and various different ways of generating workloads on real clusters too. We've got a lot of work to do before we get really good test coverage, and we can be sure that on a day when Ronnie rolls a new release and we don't have, and Ronnie hasn't had his morning cup of coffee, we've got a long way to go before we can be sure there are no regressions. Does anyone have any questions that they thought haven't been worth asking up until now? Sir? I can repeat the question.
Okay. I was just wondering if the static library testing was the only thing that put you off it was that you have to not have static functions in your code.
So using a shared library. So was the only thing that put us off using a shared library that we couldn't have static functions that we wanted to test. Yes and no. Once we thought of using a shared library, then we thought, we might as well build a shared library or, a library of some sort and use it for actually building CTDB. And if it's a shared library, will there be a performance impact? How big will it be? Will we notice it? Will we have to complicate our build system to build CTDB, to build most of the C files two different ways? And we thought of all that, and then when Rusty, and that's what I wanted to talk about with Rusty because he's a smart guy and gets good ideas. And yeah, he just suggested hash including everything, and we just went, I just went, yeah, let's try it. Let's see how hard it is. And because CTDB is a pretty big code base and it's sort of moved along over time, I thought we'd have lots more static function clashes, but it was pretty trivial. Time. Well, no, we've still got 10 minutes for questions and to party, but nobody has any questions because we've answered them. Oh, you were stretching, sir? So you don't have a question? No, that's good.
I do have a question to help on now.
You'll have to make one up. You'll be forced to. We'll turn the camera.
Any further questions?
We said it wasn't going to be rocket science. Come on.
There we go.
Well, thank you very much for that presentation, Ronnie and Martin.
We didn't have a fist fight.
I want everyone to give them a round of applause for making something perhaps a little bit more trivial, a little bit closer. We also have a small gift of our appreciation from Linux.conf.au Ballarat. You mentioned you had lots of penguins.
Yes.
Well, you actually have another penguin.
Thank you. This is going straight to the penguin cabinet.
There we go. They can go to the penguin cabinet. That is a glass penguin plated in local Ballarat gold. There you go. Thank you very much for your attendance, everybody. See you very shortly at the next session in about 15 minutes' time. Okay.